Well, it's true, isn't it, that computers are absolutely everywhere in our world. We can't do anything without using them. If we switch on the DVD player, there's a computer inside there. If we switch on the microwave, there's probably a computer inside there. When you talk to your friends, you may do it with a computer, or you may do it with your mobile phone, and that has a computer inside it as well. This amazing winged building here has computers inside it controlling the temperature and the air and so on. And talking of wings, of course, it's amazing to be here in Duxford at the Imperial War Museum, surrounded by these aeroplanes, some with great histories, and also computers are critical there. So I don't know if you've seen the Eurofighter Typhoon over here. That actually is a little bit of a scary machine, because when you pull the levers inside that machine, if you happen to be in the cockpit, any of you going to try this out afterwards? If you're in the cockpit, you pull the levers, actually there's nothing connecting the levers to the critical surfaces of the aeroplane, the elevators and ailerons and so on. It's all done by computers and by electronics, fly-by-wire they call it. And just to be completely sure, they quadruplicate the systems. So that is to say, there are 4 lots of computers and 4 lots of wires, 4 lots of everything, so that you've got 3 chances for things to break before you're really in trouble. And actually, that aeroplane relies so heavily on its computers that without the computer control, you simply wouldn't be able to fly. It doesn't matter how cool you think you are at computer games, without the computers to control the plane, this plane is completely unflyable. It would just go unstable in seconds. It would be upside down and all over the place. It just can't be done without the computer. So, yes, computers are in everything we do. And here is, as I said, our laboratory not very far away, 6 miles away or so in Cambridge, where Microsoft Research investigates many different issues to do with computing and looks at many different inventions. Actually, we have laboratories all around the world. So you see, the sun never sets on Microsoft Research. We have laboratories in China, in India, all over Europe, all over the US. Doesn't matter what the time of day is, there's some people somewhere around the world doing Microsoft Research. So what is it that we're trying to do? Well, there are 3 different things that we aim to do in Microsoft Research. First of all, we try to, as I said, make new inventions in computing to understand better what it is computers can do and what it is they can't do. The kinds of people that work in our lab, actually it's people just like you, except probably they have to be, well, there are a few people just like me, old professors, but there are some people who are only maybe 12 or 14 years older than you. So you can perhaps imagine yourselves when you finish school and then you've been to university and then you have to do something which they call taking a doctorate in philosophy. It sounds very grand and old-fashioned, but what it means is that when you're, maybe in your early 20s, 21 or so, you get to investigate a little piece of computer science all of your own and maybe invent something that nobody in the world has ever invented before. And when you've done that, you get presented with a scroll, and this proves that you got your doctorate of philosophy, and when you get to that stage, maybe in Microsoft Research, we will hire you, and you can come and do science with us, inventing new ideas in computer science. So that's what we do. A lot of invention, and then when we've done the invention, our ideas quite often go into parts of the Microsoft business. So maybe if you buy Microsoft Office, yes, for sure, that has some things from Microsoft Research invented in our research laboratory inside Office. And if you go online and you go to Bing and search, there are lots of inventions in there. And if you use the Xbox, we have a lot of inventions that have gone from our research lab that I just showed you here into those inventions. And then lastly, we try to see far into the future. What are businesses like Microsoft going to be doing in 10 and 20 years? Nobody really knows, but we have some crazy ideas which we're looking into and which you'll hear about today, which one day might just be part of the main business of Microsoft. So here we are. Here are some pictures of people. Actually, you're going to see some of these people today. See if you can, you'll have to see if you recognize any of the people in these pictures who do research in our lab. Now, we've got quite a busy program today. It's so busy and so dense that I bet you can't read it from there, but you can see that every 20 minutes something new will happen. So here's me at 10 o'clock, and every 20 minutes you're going to get a new topic in computing, and I'm going to give you a whistle-stop tour of the different things that you're going to hear about. In the middle, you'll be relieved to hear, just when you're beginning to get tired and wonder if you can concentrate anymore, thank goodness there's going to be lunch. And during lunch, there'll also be lots of live demos, things for you to play with, and people who've invented them for you to talk to. So you can ask them exactly how did they do those inventions. So what have we got during the day? Well, first is, right after me, Tori Grapel, who is an expert on machine intelligence, and he's used his expertise in machine intelligence particularly to invent things for Xbox. So when you go on Xbox Live and you play a game which is in competition with the rest of the world, there's a system there that works out how far up the rankings you should go. And Tori and his colleagues invented that. And they also invented a version of the game of Go. Do you know the game of Go? Stick your hand up in the air if you've ever heard of it. A few people have, but you've heard of chess, haven't you? Put your hand up if you've heard of chess. Oh, yes, we've all heard of chess. Well, Go is a little bit like a sort of supersized version of chess with different kinds of... the pieces are actually a bit simpler, but the board is rather bigger. And so Tori and his colleagues did that. And lastly, most recently, they've invented a game which you play on Facebook called Project Waterloo, and I think he's going to tell you all about that. What have we got next? Well, Jasmine Fisher is, believe it or not, a neuroimmunologist. That's somebody who works on how the brain works and how the nervous system works and how that interacts with your immune system, which is what protects you from disease. And Jasmine is one of a new generation of researchers who are combining biology and computer science. And this is, I think, going to be one of the big things for the future of companies like Microsoft, where at the moment we program silicon chips. In the future, we're going to be programming fragments of the human body and the DNA, which you perhaps have heard about, which is the basic building block of the human body. And Jasmine is going to tell you about some of the analyses she's doing, which help us understand how cells in the human body work. In a way, they work surprisingly a little bit like computers. That's what she's going to talk to you about, and that could be very important in understanding disease and how that works. Next, we have some visiting academics from the University of Southampton, so they're not actually in Microsoft Research, but they've come to tell us about their work on atmospheric science, and they try to understand, use computers to understand how aircraft should be designed, how flight works, especially at very high altitudes where the air is very thin. And what you see in the picture there is a balloon that they use to investigate the properties of the upper atmosphere. So the balloon goes way up there, and the little blob at the bottom there is a little package of sensors that works out what's happening high up in the atmosphere. Next, we have Robin Freeman, who is both Microsoft Research, works with us, and also at University College London, and he does wonderful work attaching tiny little computer devices to birds, and so that the progress of these birds and their behavior can be tracked and reported back, and experimenters can analyze what the birds are doing and how they behave together, for example, when they migrate. It's an amazing mystery how on earth birds know where to go thousands of miles when they migrate, and that's something which scientists like Robin are trying to understand. And having these tiny little computer devices that you can fit onto animals makes a tremendous difference in how we understand animal behavior. What's next? Next we have Samin Ishtiaq. He works in Microsoft Research. Before he worked with us, he worked with another company in Cambridge. I don't know if you've heard of it. It's called ARM. Anybody heard of that? Yeah, quite a few people have heard of ARM. And where do you find ARM computers? Actually, it turns out there are more ARM computers in the world than any other kind of computer. There is more than one ARM computer for every person on the planet. That is more than 7 billion ARM computers. I'm not sure they're very fairly shared around. I think some people have more than one and some people don't have any at all. But still, in principle, there's one each. And Samin used to work for ARM using mathematics to try to understand why it is that computers sometimes go wrong and how it is that you can use mathematics to stop computers going wrong in that way. And since he moved from ARM to Microsoft, he's trying to work the same tricks now on Windows. And here you see a fragment of Windows code, which is actually simulating the motion on the surface, I think, of a liquid. And so he's trying to use his mathematical logic. He'll tell you a little bit more what this means when he comes up here to understand exactly how it is that these that programs like that can go wrong and can go right. Of course, we want them to go right. Well, lastly, I want to mention Kinect for Xbox. This is something where my lab in the one that I showed you at the beginning, the Microsoft Research Lab here in Cambridge, had a major role in making this work. How many of you have seen Kinect for Xbox? Quite a lot of you. And for those of you who haven't, we have it here in the demos, which you'll see over lunchtime. But in the meantime also, we're going to tell you a little bit about it here. So the Kinect for Xbox is a special kind of camera. This thing here is the Xbox, if you didn't know what that looked like. And this bit here is the camera. And it's got 3 eyes, you see. And its 3 eyes are doing something rather special. They enable the camera to see in 3D. So you may have noticed that your friends have 2 eyes. You wonder why they bothered. I mean, why not just go around the world with 1 eye? Surely 1 would be enough. But actually, it turns out the second one is pretty useful because it helps us to see in 3D. And just in the same way we can see in 3D with our 2 eyes, so the Kinect uses its multiple eyes to see in 3D. So just before we do the demo, I just want to tell you a little bit about what we had to do to make Kinect work. So the thing about recognizing what the human body is doing, which is what Kinect does, is that human bodies can do so many different things. So it's very difficult to tell a computer exactly how a human body will look. Look how many different crazy shapes the human body can make, and somehow Kinect has to understand all of that. And also, human bodies come in different sizes. There are the very fit ones, and there are the not quite so fit ones, and Kinect has to understand them all. And different ages, small ones and tall ones, old ones and young ones, ones swinging handbags with short dresses and long trousers, and ones that are hidden in the undergrowth. I'm not sure if even Kinect will manage that, but you can see, in principle, how difficult it is to make this kind of thing work. And people partying together and getting in one another's way, and the Kinect camera has to sort all that out. So what we had to do was we had to show the Kinect camera when it was learned a little bit like a baby. It took many weeks and months for the Kinect to learn to see, just like babies do. And in that time, we showed it many, many different humans in many, many different shapes. Actually, this many. More than 1 million different examples of humans and their size and shape. Well, so I'm going to finish my part of the session with a demo of what we call Kinect Fusion. And my colleagues, Otmar Hillegas and David Kim here, are going to show us how Kinect Fusion works. So,
all right. So Kinect Fusion turns the Kinect around. Usually Kinect is used as a game controller on the Xbox. Here, my colleague David holds the Kinect camera in his hand, and we use the camera as a 3D scanner. So we're using the data that comes off this camera to track its position in 3D, so the computer knows where the camera is. And once we have the position in space of this camera, we can take the incoming depth frames, the incoming images from the Kinect camera, and fuse a 3D model of the world. And this allows us to scan in environments in seconds rather than minutes.
Who should we scan, Otmar?
I guess we're scanning the crowd.
We need a volunteer, I think. Is it? Who was? Here's one.
Okay.
Yes, you? Yeah, absolutely.
Yeah, come on.
I don't know your name, otherwise I'd say it. What is your name? Alex has bravely volunteered to be scanned. He's going to be the first to sit in this seat. Does it hurt, Otmar, at all?
It doesn't hurt. No,
it doesn't. That's a relief.
We probably want one more.
One more. Somebody further. The girl in the white shirt there. Yes, you. White shirt, yes. So while we're doing the scanning over here, what's your name?
Eleni.
Eleni. Excellent. You're next for scanning, or all at once?
Yeah, all at once.
All at once.
Have a
sit
seat.
down.
All right. You gotta hold still for a second, like in black and white photography.
Sitting still, that's incredibly difficult, isn't it, Otmar?
Yeah, it is.
Can kids do that? I didn't know they could.
These two are very good.
They're very still, aren't they? They're almost like statues.
All right. So first we're gonna scan them in. This time in color, actually. So it looks a little more like regular video, but this again is a 3D scan of the two.
Looks like you carved them out of rock here.
Yeah, and then I don't know if these had a shower already this morning. They're smiling, so yes, they probably had a shower. We're going to give them another one, though.
Oh, that's so messy. Oh, yuck.
So what we're doing here is we're running a physics simulation in real time of the 3D model that we generated. This is a fairly simplistic thing that we're doing. We're just shooting these little spheres into the scene, and they bounce off the scan of these two kids who I think have deserved a round of applause now.
Hey.